Bohr's model of the atom, a revolutionary step in atomic theory in the early 20th century, the field of atomic physics was a landscape in flux. Classical mechanics, which had governed physics for centuries, was unable to explain certain phenomena observed in atomic and subatomic systems. The behavior of electrons in atoms, in particular, posed a major challenge. One of the most famous contributions to this field came from Danish physicist Niels Bohr, whose atomic model revolutionized our understanding of atomic structure. His theory not only explained previously unexplained features of the hydrogen atom, but also set the stage for the development of quantum mechanics. The need for a new model before Bohr's groundbreaking work, the dominant atomic theory was based on the ideas of John Dalton, J. Thomson, and Ernest Rutherford. In Dalton's atomic theory, atoms were considered indivisible particles, the basic units of matter. J. Thomson's discovery of the electron in 1897 led to his proposal of the plum pudding model, where the atom was seen as a cloud of positive charge with negatively charged electrons embedded in it, like raisins in a pudding. However, this model failed to explain the atom's stability and structure, particularly its spectral characteristics. Ernest Rutherford's gold foil experiment in 1909 showed that the atom was mostly empty space with a dense, positively charged nucleus at its center. This led to the development of Rutherford's nuclear model, in which electrons orbited the nucleus in a manner similar to how planets orbit the Sun. However, Rutherford's model still did not fully explain several important phenomena, such as why atoms emitted light at specific wavelengths, or what determined the stability of an atom. These gaps in understanding created a pressing need for a more comprehensive theory of atomic structure. Bohr's radical proposal in 1913, Niels Bohr, then a young physicist working in Rutherford's laboratory, made a revolutionary proposal to address these issues. Building upon Rutherford's nuclear model, Bohr suggested that electrons did not move in arbitrary orbits around the nucleus, as Rutherford had assumed, but rather occupied specific, quantized orbits. These orbits corresponded to fixed energy levels, and electrons could only exist in these discrete orbits without radiating energy. Bohr's key insight was the application of the concept of quantization, a novel idea at the time, to the behavior of electrons. Bohr's model was based on three postulates which set it apart from previous atomic theories. Electrons move in fixed, circular orbits around the nucleus, and these orbits are characterized by quantized angular momentum. Electrons in these orbits do not radiate energy, even though they are accelerating due to their circular motion. This was a radical departure from classical electrodynamics, which predicted that any accelerating charge should emit electromagnetic radiation and lose energy. Electrons can only absorb or emit radiation when they jump between these fixed orbits. The energy difference between the orbits corresponds to the frequency of the radiation emitted or absorbed, explaining the discrete spectral lines observed in atomic spectra. Bohr's quantization of angular momentum, the key to understanding Bohr's model, lies in the concept of quantization. Bohr postulated that the angular momentum of an electron in orbit around the nucleus was quantized, meaning it could only take on certain discrete values. Specifically, the angular momentum of an electron in the th orbit is given by where is a positive integer, the quantum number, and is the reduced Planck's constant. This idea of quantization was inspired by Max Planck's work on blackbody radiation and Albert Einstein's explanation of the photoelectric effect, both of which introduced the notion that energy is quantized in discrete packets quanta. Bohr applied this principle to the motion of electrons in the atom, arguing that only those orbits for which the electron's angular momentum is an integer multiple of are stable and allowed. In essence, Bohr's model broke away from the classical view of continuous energy levels and embraced the idea that certain energies are forbidden and others allowed. This allowed the electron to occupy only specific, discrete energy levels, leading to stable orbits without radiation emission. Explaining the hydrogen spectrum, one of the major successes of Bohr's model was its ability to explain the spectral lines of hydrogen. Before Bohr, scientists had observed that hydrogen atoms, when excited, emitted light at specific wavelengths. These lines, known as the hydrogen spectrum, were puzzling because they did not fit the predictions of classical physics. Bohr's model explained this by suggesting that when an electron in a hydrogen atom absorbs or emits energy, it does so by jumping between quantized orbits. The energy difference between these orbits corresponds to the energy of the emitted or absorbed photon. Using this idea, Bohr was able to calculate the wavelengths of the spectral lines of hydrogen. For example, the transition of an electron from the orbit to the orbit in a hydrogen atom corresponds to the emission of ultraviolet light, which is observed in the Lyman series of the hydrogen spectrum. Similarly, transitions to higher orbits correspond to visible light, Balmer series, and infrared light Paschen series. The wavelengths of the spectral lines in each series were found to match the predictions made by Bohr's model, a remarkable success. This provided strong evidence in favor of Bohr's quantization scheme and marked a major triumph for the model. The Bohr model and atomic stability, another significant contribution of Bohr's theory, was its explanation of atomic stability. In classical physics, an electron moving in a circular orbit should continuously lose energy due to electromagnetic radiation, causing it to spiral inward and eventually crash into the nucleus. This was not observed in practice, as atoms appeared to be stable, with electrons remaining in fixed orbits. Bohr's model resolved this paradox by postulating that electrons in quantized orbits did not radiate energy, thereby preventing the electron from spiraling into the nucleus. In this way, Bohr's model accounted for the stability of atoms. Limitations of Bohr's model. While Bohr's model was groundbreaking and successful in explaining the hydrogen atom, it had significant limitations. For one, it only worked well for hydrogen, the simplest of atoms. For more complex atoms with multiple electrons, Bohr's model failed to accurately predict the spectral lines. This limitation arose because Bohr's model could not account for the interactions between multiple electrons in an atom, nor did it consider the wave nature of electrons. Moreover, Bohr's assumption that electrons follow circular orbits was eventually shown to be incorrect. The advent of quantum mechanics in the 1920s, particularly the work of Schrödinger and Heisenberg, revealed that electrons do not follow defined orbits, but instead exist in probability clouds, with their positions and velocities governed by wave functions. This development led to the abandonment of Bohr's model in favor of the more complex and accurate quantum mechanical model. Legacy and influence despite its limitations, Bohr's model was instrumental in shaping the development of atomic theory. Bohr's work laid the foundation for the later development of quantum mechanics and quantum electrodynamics. His ideas about quantization inspired the work of scientists like Werner Heisenberg, who developed the uncertainty principle, and Erwin Schrödinger, who formulated the wave equation that described electron behavior probabilistically. Bohr's model also led to the development of the concept of quantum jumps, or discrete transitions between energy levels, which became fundamental to the understanding of atomic and molecular spectra. This idea of quantized transitions has had profound implications not only in atomic physics, but also in fields such as chemistry, where it helps explain the behavior of atoms in chemical reactions. Furthermore, Bohr's work on atomic structure had practical consequences. His model paved the way for the development of technologies such as lasers, semiconductors, and other devices that rely on quantum mechanical principles. The creation of modern quantum technologies, including quantum computers and quantum encryption systems, can trace their roots back to the work done by Bohr and his contemporaries. In conclusion, Niels Bohr's atomic model was a revolutionary advancement in our understanding of the atom. By introducing the concept of quantized orbits and explaining the discrete spectral lines of hydrogen, Bohr provided a framework that successfully addressed many of the challenges faced by previous atomic models. Though later developments in quantum mechanics replaced Bohr's model, its contributions to atomic theory remain foundational. Bohr's work not only reshaped the way we think about the structure of atoms, but also set the stage for the quantum revolution that would transform physics, chemistry, and technology in the 20th century and beyond. Electron quantization, the birth of discrete energy in the atomic world at the dawn of the 20th century, physics stood at a crossroads. Classical ideas, which had successfully explained the motion of planets, the flow of electricity, and the behavior of machines, began to fail when scientists looked deeper into the atom. One of the most puzzling questions concerned the behavior of electrons. Why did atoms emit light only at specific colors? Why were atoms stable instead of collapsing under their own electrical forces? The answer to these mysteries emerged through a radical idea that challenged centuries of continuous thinking: the quantization of the electron. Electron quantization refers to the concept that electrons in atoms can possess only specific, discrete amounts of energy rather than a continuous range. This idea was deeply counterintuitive at the time. In everyday life, energy appears smooth and continuous. A rolling ball can have any speed. A moving car can have any amount of kinetic energy. But inside the atom, nature behaved differently. Energy came in steps, not slopes, and electrons were bound by strict quantum rules. The roots of electron quantization can be traced back to a growing crisis in classical physics. By the late 1800s, experiments involving light and matter were producing results that defied traditional explanations. One of the most troubling problems was blackbody radiation. Classical theory predicted that a hot object should emit infinite energy at short wavelengths, a result famously known as the ultraviolet catastrophe. This contradiction between theory and experiment forced physicists to reconsider their assumptions about energy itself. In 1900, Max Planck proposed a desperate but brilliant solution. He suggested that energy was not emitted continuously, but in small, discrete packets he called quanta. According to Planck, the energy of these packets was proportional to the frequency of radiation, introducing a fundamental constant of nature now known as Planck's constant. At first, Planck viewed this as a mathematical trick rather than a statement about reality, but it would soon reshape physics forever. Albert Einstein took Planck's idea seriously and extended it in 1905 to explain the photoelectric effect. He argued that light itself was quantized, made up of particles later called photons. These photons could eject electrons from metal surfaces only if they possessed enough energy, regardless of the light's intensity. This provided strong evidence that energy exchange at the atomic level was fundamentally discrete. Still, the internal structure of atoms remained mysterious. It was Niels Bohr who made the bold leap of applying quantization directly to the electron inside the atom. In 1913, Bohr proposed that electrons orbit the nucleus, but can exist only in certain allowed energy states. These states were not arbitrary. They were fixed, quantized levels determined by fundamental constants of nature. An electron could not exist between these levels, just as a person cannot stand between the rungs of a ladder. According to Bohr's model, each allowed orbit corresponded to a specific energy. When an electron occupied one of these orbits, it remained stable and did not radiate energy. This was a radical departure from classical electromagnetism, which predicted that an accelerating charge, such as an orbiting electron, should continuously emit radiation and lose energy. If that were true, atoms would collapse in a fraction of a second, but atoms clearly endured. Quantization provided the missing explanation. Electron quantization also explained a long-standing mystery in spectroscopy. When atoms are heated or energized, they emit light at specific wavelengths, producing distinct spectral lines. Hydrogen, the simplest atom, displays a series of sharp lines rather than a continuous rainbow. Classical physics could not account for this selectivity. Bohr's quantized energy levels offered a precise explanation. In Bohr's framework, when an electron absorbs energy, it jumps from a lower energy level to a higher one. When it returns to a lower level, it releases energy in the form of a photon. The energy of this photon is exactly equal to the difference between the two energy levels. Because only certain energy levels are allowed, only certain photon energies, and therefore wavelengths, can be emitted. This directly matched the observed spectral lines of hydrogen with remarkable accuracy. For the first time, the atomic spectrum was no longer a mystery, but a fingerprint of electron quantization. Each line represented a specific quantum jump, a transition between two discrete states. This idea transformed spectroscopy from a catalog of experimental data into a powerful tool for probing atomic structure. Through spectral lines, scientists could now see the hidden quantum architecture of matter. Electron quantization also introduced a new way of thinking about stability in nature. In classical systems, stability often arises from balance and continuous adjustment. In the quantum world, stability emerged from restriction. Electrons were stable because they were forbidden from losing energy continuously. Only specific transitions were allowed, and unless sufficient energy was supplied, an electron simply stayed where it was. This rule-based stability became a defining feature of quantum systems. As experimental techniques improved, it became clear that electron quantization was not limited to hydrogen alone. More complex atoms also exhibited discrete spectra, though their patterns were richer and more complicated. While Bohr's original model struggled to explain these heavier atoms in detail, the principle of quantized energy levels remained intact. It was not the idea of quantization that was flawed, but the simplistic picture of circular orbits. The development of quantum mechanics in the 1920s refined and deepened the concept of electron quantization. Physicists like Erwin Schrödinger and Werner Heisenberg replaced the idea of precise electron paths with mathematical descriptions based on wave functions and probabilities. In this new framework, electrons no longer traveled in neat orbits, but occupied quantized states described by solutions to Schrödinger's equation. Yet even in this more advanced theory, quantization remained central. the allowed solutions of the wave equation corresponded to discrete energy levels, just as Bohr had proposed. The difference was that these levels were now associated with orbitals, regions of probability rather than fixed paths. Electron quantization survived the transition from early atomic models to full quantum mechanics, emerging stronger and more universal than before. One of the most profound implications of electron quantization is its role in shaping the physical and chemical properties of matter. The arrangement of electrons in quantized energy levels determines how atoms bond, how molecules form, and how materials behave. The periodic table itself is a direct consequence of electron quantization, with repeating patterns arising from the filling of discrete electron shells. In solids, electron quantization gives rise to energy bands, separating conductors, insulators, and semiconductors. The modern world of electronics, from transistors and microchips to smartphones and computers, rests entirely on these quantum principles. Without quantized electron energies, there would be no controlled flow of electricity, no digital revolution, and no information age. Electron quantization also plays a crucial role in modern technologies such as lasers. In a laser, electrons are excited to higher energy states and then stimulated to drop to lower states in a coordinated way, emitting coherent light of a single wavelength. This precise control over electron transitions is only possible because energy levels are discrete and predictable. Beyond technology, electron quantization has reshaped our philosophical understanding of nature. It revealed that the universe at its most fundamental level is not smooth and continuous but granular and rule-bound. Energy, once thought to flow freely, is now understood to move in jumps. Change, at the quantum level, happens not gradually but suddenly. This idea continues to challenge human intuition. Even today, the notion that an electron cannot exist between energy levels feels strange. Yet experiment after experiment has confirmed this behavior with astonishing precision. Quantum theory, built upon electron quantization, has become one of the most successful scientific frameworks ever developed, matching observation to theory to an extraordinary degree. In retrospect, electron quantization marks the true beginning of the quantum revolution. It was the moment when physicists realized that the microscopic world obeys laws fundamentally different from those of everyday experience. Bohr's daring application of quantization to the atom transformed a theoretical curiosity into a physical reality, opening the door to an entirely new vision of matter. As documentaries trace the history of modern science, electron quantization stands out as a turning point, a quiet but profound shift in thinking that redefined atoms, energy, and the structure of reality itself. From glowing hydrogen tubes in early laboratories to the quantum technologies shaping the future, the story of electron quantization is the story of how humanity learned that nature, at its core, counts in whole numbers. In the early 20th century, physicists were engaged in a deep and transformative exploration of the atom. The old, classical laws of physics that governed macroscopic phenomena no longer seemed to be sufficient for explaining atomic and subatomic behaviors. Atoms were not just simple entities that could be explained by classical mechanics, and a revolution was brewing that would completely redefine our understanding of matter and energy. This revolution was encapsulated by the emergence of quantum mechanics, and one of the most fundamental shifts in thinking came with the discovery of wave-particle duality. This duality, first proposed by the French physicist Louis de Broglie, suggested that not only light, as was previously thought, but also particles such as electrons could exhibit both wave-like and particle-like properties, a concept that would forever change the landscape of physics. Prior to the development of quantum mechanics, light was understood to be a wave phenomenon, an idea solidified by the work of Thomas Young and Augustin Jean Fresnel in the 19th century. The famous double-slit experiment showed that light could interfere with itself, producing patterns of constructive and destructive interference, a behavior typical of waves. Additionally, James Clerk Maxwell's equations, which described electromagnetism, treated light as an electromagnetic wave propagating through space. However, light also exhibited characteristics that couldn't be explained solely through wave theory. One of the key phenomena that challenged the wave-only view of light was the photoelectric effect, which Albert Einstein explained in 1905. In the photoelectric effect, light shining on a metal surface could eject electrons from the metal, but only if the light's frequency exceeded a certain threshold, regardless of its intensity. Classical wave theory couldn't account for this, since it predicted that even low-frequency light, if sufficiently intense, should be able to release electrons. Einstein's proposal that light could also behave as discrete packets of energy, which he called quanta, or photons, was a revolutionary breakthrough that led to the development of quantum theory. This idea of light having a dual nature capable of exhibiting both wave-like and particle-like properties was the beginning of what would become known as wave-particle duality. But this concept didn't remain exclusive to light alone. In fact, the very nature of matter would soon be shown to be similarly complex. In the 1920s, Louis de Broglie, inspired by Einstein's work on the photoelectric effect and Max Planck's work on energy quanta, extended the wave-particle duality concept to matter, particularly electrons. His hypothesis was both audacious and elegant. If light could behave as both a wave and a particle, then perhaps particles like electrons, which were previously understood solely as discrete entities, might also display wave-like behavior under certain circumstances. De Broglie's hypothesis was rooted in the idea that any particle with momentum should be associated with a wave. Specifically, he proposed that the wavelength of a particle could be related to its momentum through the famous de Broglie relation, where is Planck's constant. This was a radical departure from the classical view of particles. According to de Broglie, just as light has a wavelength and frequency, matter could also exhibit properties of waves, depending on the momentum of the particle. For example, an electron moving through space was not just a point-like particle. It also had a wavelength associated with its motion. This wave behavior was not immediately obvious because the wavelength associated with massive particles is typically very small, but de Broglie's insight paved the way for a fundamental shift in how particles and waves were understood to interact. One of the first confirmations of de Broglie's hypothesis came from the work of Clinton Davison and Lester Germer in 1927. They conducted an experiment in which they directed electrons at a crystal and observed that the electrons diffracted, much like light waves would. This diffraction pattern was a direct confirmation that electrons, particles, could behave like waves under certain conditions. The discovery of electron diffraction was a monumental step in validating de Broglie's wave-particle duality for matter. It provided the experimental foundation for what would soon become a cornerstone of quantum mechanics. The idea of wave-particle duality profoundly altered the way scientists thought about particles and waves. Classical physics, especially Newtonian mechanics, treated particles and waves as entirely separate phenomena. Particles, like billiard balls, were discrete and had definite positions and velocities at any given time. Waves, on the other hand, were continuous and spread out, exhibiting interference and diffraction. Wave-particle duality shattered this binary view, showing that entities at the atomic and subatomic scale could exhibit both types of behavior, depending on the situation. This duality was further developed by the work of Werner Heisenberg and Erwin Schrödinger, whose contributions laid the groundwork for quantum mechanics. Heisenberg, in particular, formulated the uncertainty principle in 1927, which stated that it is impossible to simultaneously know both the exact position and momentum of a particle. This was a direct consequence of the wave-like behavior of particles. To pinpoint the position of a particle, you had to interact with it in a way that altered its momentum, and vice versa. This uncertainty was not due to limitations in measurement or instrumentation, but rather an intrinsic feature of the quantum world. It reflected the profound difference between classical and quantum systems, where the act of measurement itself could affect the system being measured. Meanwhile, Schrödinger developed his famous wave equation in 1926, which described how the wave-like properties of particles could be mathematically modeled. The Schrödinger equation provided a way to calculate the probability distribution of where a particle, such as an electron, might be found in space. This was a fundamental shift from the classical view, where particles were thought to have definite positions and trajectories. In Schrödinger's quantum world, particles were described by wave-functions, mathematical functions that gave the probability of finding a particle in a particular place at a particular time. In this new framework, particles like electrons were no longer seen as individual points, but as probability waves that described regions of space where they were likely to be found. These waves were governed by the Schrödinger equation and could exhibit interference, just like waves of light. The behavior of these waves depended on the boundary conditions of the system they were in, such as the potential energy of the system or the constraints imposed by the surrounding environment. The wave function itself did not provide a definite location for the particle, but rather a distribution of probabilities. For example, an electron in an atom might have a high probability of being found near the nucleus, but there is also a small chance it could be found much farther away. Wave-particle duality became one of the key principles of quantum mechanics, guiding not only our understanding of atomic structure, but also the behavior of all particles at the microscopic scale. The dual nature of electrons and other particles like protons and neutrons meant that they could no longer be treated as classical particles. Their behavior was governed by probabilistic laws, and their interactions with other particles were governed by wave-like phenomena, including interference and diffraction. Wave-particle duality also had profound implications for how we understand energy. In classical physics, energy was often thought of as a continuous quantity that could take on any value. But in quantum mechanics, energy itself became quantized. The energy levels of electrons in an atom, for example, were not continuous but discrete, and the transitions between these levels resulted in the emission or absorption of photons with specific energies. These discrete energy levels, along with the wave-like nature of particles, formed the basis of quantum theory. As quantum mechanics developed, wave-particle duality continued to influence both theoretical and experimental physics. It not only offered explanations for phenomena such as electron diffraction and the photoelectric effect, but also helped to underpin the development of modern technologies like semiconductors, lasers, and quantum computers. The principle of wave particle duality is integral to the functioning of many of these technologies, where particles and waves are treated as interchangeable depending on the situation. The development of quantum mechanics, with its revolutionary ideas like wave, particle duality, ultimately led to a deep rethinking of the physical universe. In the classical view, particles and waves were separate and distinct phenomena, but quantum mechanics showed that at the subatomic level, this distinction no longer holds. Instead, the wave-particle duality illustrated the inherent complexity and richness of the quantum world, one where entities could exist simultaneously as particles and waves, and where the fundamental nature of reality was probabilistic rather than deterministic. This duality not only challenged long-held assumptions about the nature of matter and energy, but also opened the door to new realms of scientific exploration and technological innovation. In 1927, Werner Heisenberg, a German physicist, introduced a concept that would revolutionize the way scientists understood the microscopic world: the uncertainty principle. This principle stated that it is fundamentally impossible to simultaneously know both the position and momentum of a particle with absolute precision. The more accurately one of these properties is measured, the less precisely the other can be known. This seemingly simple idea would have profound implications for the philosophy of science, the foundations of quantum mechanics, and our general understanding of reality itself. The uncertainty principle was one of the most radical departures from classical physics, which had always assumed that, in principle, all physical quantities, such as position, velocity, and energy, could be measured with arbitrarily high precision. In classical mechanics, if one knew the current position and momentum of an object, the future behavior of that object could be predicted with perfect accuracy. The notion that there could be limits to what could be known, even in principle, about a physical system was deeply unsettling to many physicists at the time. To understand the significance of the uncertainty principle, it is important to first explore the classical view of measurement and observation. In classical physics, a system could be described with a set of parameters, such as the position and velocity of an object, and these parameters could be measured with increasing precision as technology advanced. If one could measure an object's position precisely, for example, one could also determine its velocity and, in turn, predict its future position and velocity with high accuracy. In essence, classical physics operated on the assumption that the world was deterministic, meaning that every event or state of affairs was the result of a preceding cause, and that with enough information, everything could be predicted. However, in the quantum world, things were fundamentally different. When Heisenberg introduced the uncertainty principle, it wasn't just a theoretical abstraction. It was rooted in the very nature of quantum systems. The uncertainty principle is not a result of technological limitations or experimental inaccuracies. It is a reflection of the intrinsic properties of quantum particles. In fact, the principle is a direct consequence of the wave-like nature of particles, which had been established by the earlier work of scientists like Louis de Broglie and Erwin Schrödinger. The more we know about the wave-like properties of a quantum system, such as its momentum, the less we can know about its particle-like properties, such as its position, and vice versa. Heisenberg's uncertainty principle can be expressed mathematically as where represents the uncertainty in position, represents the uncertainty in momentum, and is Planck's constant. The inequality shows that the product of the uncertainties in position and momentum is always greater than or equal to a constant value. The more precisely we measure one of these quantities, the larger the uncertainty in the other, This limit is not a consequence of measurement error, but a fundamental feature of the quantum world. The uncertainty principle has far-reaching consequences. One of the most important is that it challenges the classical notion of determinism. In classical mechanics, the state of a system at any given time is enough to predict its future evolution with complete certainty. In contrast, quantum mechanics, with its uncertainty relations, suggests that there are inherent limitations to what we can know about a system at any given moment. While we can calculate the probability distribution of where a particle might be located or what its momentum might be, we can never know both with complete precision at the same time. This shift from determinism to probabilistic descriptions of nature was a fundamental departure from classical thinking. In quantum mechanics, the future is not fully determined by the present state of a system. Instead, it is described in terms of probabilities, with wave functions providing the likelihood of finding a particle in a particular state. Heisenberg's uncertainty principle directly reflects this probabilistic nature. It forces us to abandon the idea that we can have complete knowledge of the precise state of a system at all times. One of the key implications of the uncertainty principle is the idea that measurement itself influences the system being measured. In classical physics, measurements were assumed to be passive. That is, they did not disturb the system being observed. However, in quantum mechanics, the act of measuring a system inevitably alters its state. For example, to measure the position of an electron, one must interact with it in some way, typically by scattering light off of it. This interaction inevitably disturbs the electron's momentum, leading to an increase in uncertainty about its momentum. Similarly, measuring the momentum of an electron with great precision would cause a corresponding uncertainty in its position. This interaction between the observer and the system is a fundamental feature of quantum mechanics and is often referred to as the observer effect. The uncertainty principle also has profound philosophical implications. It challenges the classical view of an objective reality that exists independently of observation. In the quantum world, reality seems to be inherently tied to measurement and observation. Heisenberg's principle implies that there are limits to what can be known about the world, and it suggests that the act of observation is not a neutral, passive activity, but an active one that affects the system being observed. This idea has led to various philosophical interpretations of quantum mechanics, some of which suggest that the state of a quantum system does not exist in a definite state until it is observed. This is known as the Copenhagen interpretation of quantum mechanics, which was developed by Niels Bohr and Werner Heisenberg themselves. The uncertainty principle is not limited to just position and momentum. It has broader implications for the behavior of quantum systems. For example, the energy-time uncertainty principle relates the uncertainty in the measurement of energy to the uncertainty in time. This principle suggests that energy fluctuations can occur over very short timescales, leading to the phenomenon of virtual particles that appear and disappear spontaneously in a vacuum. These fluctuations are a direct consequence of the uncertainty principle and have been experimentally observed in phenomena such as the Casimir effect, where two conducting plates placed close together experience an attractive force due to the fluctuations in the quantum vacuum. The uncertainty principle also plays a crucial role in the behavior of quantum systems on macroscopic scales. For example, the tunneling effect, in which particles pass through energy barriers that they would not be able to surmount classically, is a direct result of the uncertainty in position and momentum. This phenomenon has been observed in a variety of quantum systems, including in the operation of scanning tunneling microscopes, which rely on the ability of electrons to tunnel through small gaps to create higher-resolution images of surfaces at the atomic scale. While the uncertainty principle is a cornerstone of quantum mechanics, it does not imply that everything in the quantum world is inherently chaotic or unpredictable. Rather, it suggests that quantum systems are inherently probabilistic, and that the uncertainty we encounter is a reflection of the limitations of our knowledge about these systems. The uncertainty in position and momentum does not mean that the electron, for example, is in some kind of blurred state. Instead, it means that there are inherent limits to how precisely we can describe its state. This is in contrast to classical mechanics, where we could, in principle, describe the motion of an object with infinite precision. Heisenberg's uncertainty principle has also had a lasting impact on the development of quantum technologies. The principle is central to the operation of quantum computers, where qubits, quantum bits, are in superpositions of states that allow for parallel processing of information. The probabilistic nature of quantum mechanics is key to the power of quantum computing, as it allows for computations that would be intractable on classical computers. Similarly, the principle has applications in quantum cryptography, where the uncertainty in measurement ensures the security of communication by making it impossible to eavesdrop on quantum communication systems without being detected. The uncertainty principle has even influenced more speculative areas of physics, such as the study of the fundamental nature of space and time. Some theories suggest that the limitations imposed by the uncertainty principle may apply to the very fabric of spacetime itself. According to these ideas, at extremely small scales, the concept of location may become blurred due to quantum fluctuations, leading to the possibility of a quantum foam that underlies the smooth spacetime continuum we observe at larger scales. In conclusion, Heisenberg's uncertainty principle is not just a mathematical tool, but a fundamental insight into the nature of the quantum world. It challenges the classical notion of a fully predictable and determinate universe, and instead presents a reality in which the very act of measurement imposes limits on what can be known. It has far-reaching implications for our understanding of the universe, influencing everything from the behavior of subatomic particles to the development of cutting-edge quantum technologies. The uncertainty principle is a cornerstone of modern physics, and its impact extends far beyond the world of quantum mechanics, shaping our understanding of the very fabric of reality itself. In the 1920s, quantum mechanics was rapidly evolving, and the understanding of atomic behavior was undergoing profound transformations. One of the critical milestones in this revolution came with the work of Erwin Schrödinger, whose development of the Schrödinger equation in 1926 provided a new and powerful way to describe behavior of electrons and other quantum particles. This wave equation would not only replace the classical concepts of particle motion, but also introduce a completely new way of thinking about the nature of reality at the atomic scale. Schrödinger's equation was a response to the growing realization that the behavior of subatomic particles, like electrons, could not be described by classical physics alone. As scientists delved deeper into the atomic world, they found that the behavior of these tiny particles seemed to defy the principles of classical mechanics. Electrons, for example, did not follow well-defined paths or orbits around the nucleus, as had been proposed by Bohr in his model of the atom. Instead, they exhibited wave-like properties, as had been suggested by Louis de Broglie, and could not be pinpointed in specific locations with certainty. The classical ideas of particles moving in fixed orbits were giving way to a more complex understanding, where particles seemed to be spread out in waves of probability. The need for a new description of electron behavior arose from the increasing success of quantum theory in explaining phenomena that classical physics could not. One of the most famous examples of this was the ability of quantum mechanics to explain the discrete spectral lines emitted by atoms when energized. These spectral lines were a key feature of atomic behavior, but they could not be accounted for by classical theories. Bohr's model, which introduced quantized orbits for electrons, was successful in explaining the hydrogen atom's spectrum, but it was limited to only the simplest atom. More complex atoms with multiple electrons defied the Bohr model and required a deeper, more generalized understanding. Schrödinger's wave equation was one of the critical contributions to this new understanding. It provided a mathematical framework that allowed scientists to describe the behavior of electrons not as discrete particles, but as wave-like entities that existed in a state of probability. The equation itself is a partial differential equation, meaning that it describes how the wave function of a quantum system changes over time. The wave function is a mathematical object that encodes all the information about a system, its energy, momentum, position, and other properties. However, what makes the wave function so powerful is that it does not provide exact values for these properties, but rather gives the probability distributions for where a particle might be found and what its properties might be at any given moment. The central idea behind Schrödinger's wave equation is that particles like electrons are not confined to specific orbits, as Bohr had suggested, but instead exist in a spread-out cloud of probability. The electron's position, momentum, and other properties can only be described probabilistically rather than deterministically. In Schrödinger's view, the electron is not just a particle with a definite position, but also a wave that has the potential to be found in different locations around the nucleus. The square of the wave function, when calculated, gives the probability density of where the electron is likely to be found at a given time. This probabilistic description marked a significant departure from the classical, deterministic picture of the atom. In simple terms, Schrödinger's equation suggests that electrons, instead of moving in precise orbits like planets around the Sun, exist as a cloud of potential locations, with regions of higher probability of finding the electron at certain points around the nucleus. These regions are described by orbitals, mathematical solutions to the Schrödinger equation that define the regions in space where an electron is most likely to be found. Each orbital has a specific energy associated with it, and electrons can exist in different energy states, just as Bohr had proposed, but in a much more fluid and probabilistic manner. One of the key features of Schrödinger's equation is that it incorporates the wave-like nature of electrons. The equation itself is derived from the principles of wave mechanics and is similar in form to the classical wave equation used to describe sound waves, light waves, and other types of waves. However, Schrödinger's equation goes much further by providing a quantum mechanical description of the electron's wave-like behavior in the context of the atom. Unlike classical waves, which have a definite amplitude and frequency, the waves in quantum mechanics represent probabilities and are described by the wave function. The fact that the wave function can take on multiple values in different places and for different times is what gives rise to the probabilistic nature of quantum mechanics. Schrödinger's equation also incorporates the concept of energy quantization. Just as Bohr had proposed quantized orbits for electrons, Schrödinger's equation showed that the energy levels available to an electron in an atom are also discrete. These quantized energy levels are associated with the solutions to the Schrödinger equation, which are the allowed wave functions for the system. The quantization arises because the wave function must satisfy certain boundary conditions, which restrict the allowed values of energy and lead to the discrete energy levels observed in atomic spectra. These energy levels are a direct consequence of the wave-like nature of the electron and are a key feature of the quantum mechanical description of the atom. The development of Schrödinger's wave equation was a monumental step in the history of quantum mechanics. It provided a unified framework that could explain not only the hydrogen atom, but also more complex atoms and molecules. It allowed for a more accurate description of atomic structure and the behavior of electrons, opening the door to new areas of research and discovery. Schrödinger's equation helped to explain the formation of chemical bonds, the structure of the periodic table, and many other fundamental aspects of chemistry and physics. One of the most important consequences of Schrödinger's wave mechanics is the concept of orbitals. Orbitals are regions of space around the nucleus where the probability of finding an electron is highest. These orbitals are solutions to the Schrödinger equation and are described by a set of quantum numbers that define their size, shape, and orientation. The four quantum numbers, n the principal quantum number, L the orbital angular momentum quantum number, m the magnetic quantum number, and s the spin quantum number, provide a complete description of the electron's state within an atom. The shape of the orbitals is determined by the quantum numbers. For example, the s orbital is spherical, while the p orbital has a dumbbell shape, and the d orbital has a more complex shape. These orbitals are the building blocks of the modern understanding of atomic structure. They describe where electrons are likely to be found and how they interact with each other in chemical reactions. The development of the concept of orbitals helped to explain many of the trends observed in the periodic table and laid the groundwork for the field of quantum chemistry. In addition to explaining atomic structure, Schrödinger's equation also played a crucial role in the development of quantum field theory, the theory that describes the interactions between elementary particles. Quantum field theory is based on the idea that particles are not point-like objects, but rather excitations in underlying quantum fields. Schrödinger's equation provided the mathematical tools necessary to describe these fields and the particles associated with them. This development has had far-reaching consequences for our understanding of the fundamental forces of nature, leading to the creation of the standard model of particle physics. Schrödinger's work also had important implications for the development of technology. The principles of wave mechanics and the wave-like behavior of particles are at the heart of many modern technologies, from lasers to transistors to the magnetic resonance imaging MRI machines used in medicine. The development of quantum mechanics, based on the ideas introduced by Schrödinger and others, has revolutionized fields ranging from electronics to materials science to quantum computing. Schrödinger's equation continues to be an essential tool for understanding the behavior of quantum systems and designing new technologies that take advantage of quantum mechanical principles. Schrödinger's wave equation also highlighted the inherent limitations of classical thinking. Classical mechanics treated particles as well-defined objects with specific locations and velocities. In contrast, the quantum mechanical description of the electron as a probability wave challenged this classical view and suggested that our understanding of the world at the atomic scale must be probabilistic rather than deterministic. This realization forced physicists to rethink the nature of reality itself. The idea that the exact state of a particle could not be known with complete certainty led to new philosophical questions about the role of observation and measurement in determining the state of the universe. In conclusion, the development of the Schrödinger equation was one of the most significant advancements in the history of science. It provided a new and more accurate way to describe the behavior of electrons and other quantum particles, laying the foundation for modern quantum mechanics. Schrödinger's equation allowed for a more complete understanding of atomic structure, the formation of chemical bonds, and the behavior of quantum systems. It also introduced the concept of orbitals, which are fundamental to our understanding of chemistry and physics. Schrödinger's work continues to shape the way we think about the microscopic world, and has had profound implications for both theoretical and applied physics. The legacy of Schrödinger's wave equation is still felt today in the cutting-edge technologies that are reshaping our world. The mid-20th century witnessed a series of breakthroughs that would forever change our understanding of atomic and subatomic behavior, one of the most profound being the rise of quantum mechanics, which provided a new framework for understanding the interactions of particles at the atomic scale. A crucial part of this paradigm shift was the development of Pauli's exclusion principle, formulated by the Austrian physicist Wolfgang Pauli in 1925. This principle would not only help to explain the structure of the atom, but it would also have far-reaching consequences across many fields, including chemistry, solid-state physics, and even cosmology. The exclusion principle is grounded in the principle that no two fermions particles that obey Fermi-Dirac statistics can occupy the same quantum state simultaneously. Fermions are a class of particles that includes electrons, protons, and neutrons, which are the fundamental building blocks of matter. In essence, Pauli's exclusion principle states that two electrons in an atom, for instance, cannot have identical quantum numbers, meaning that no two electrons can have the exact same set of quantum properties. This prohibition is a direct result of the wave nature of electrons and is a consequence of the fundamental structure of quantum mechanics. To understand the significance of the exclusion principle, it is necessary to revisit the concepts of quantum mechanics that were emerging at the time. By the early 1920s, quantum theory had made great strides in explaining atomic spectra and other phenomena that classical physics could not. Schrödinger's wave equation had provided a mathematical description of electrons in terms of wave functions, and Bohr's model of the atom had introduced the idea of quantized orbits for electrons. However, the application of these concepts to more complex systems, like multi-electron atoms, posed new challenges. In particular, the question of how multiple electrons could be arranged in an atom while obeying the rules of quantum mechanics was still an open one. Pauli's exclusion principle arose in response to this challenge. The principle essentially dictates the way in which electrons are arranged in an atom. Every electron in an atom can be described by a set of quantum numbers, four parameters that specify the energy, shape, orientation, and spin of the electron's orbital. These quantum numbers are: principal quantum number n describes the energy level of an electron and is always a positive integer 1, 2, 3. Orbital angular momentum quantum number L describes the shape of the orbital and can take integer values from 0 to. Magnetic quantum number m describes the orientation of the orbital in space and can take integer values between and. Spin quantum number s describes the intrinsic angular momentum or spin of the electron, which can be or Pauli's exclusion principle stipulates that no two electrons in an atom can have the same set of quantum numbers. This means that each electron in an atom must occupy a unique state. For example, in an atom, two electrons can occupy the same energy level same and the same orbital shape same, but they must have opposite spins for one electron and for the other. This constraint is fundamental to the structure of atoms and has profound implications for the arrangement of electrons in atomic orbitals. The implications of the exclusion principle are far-reaching. One of the most direct consequences is that it explains the structure of the periodic table. In the early 20th century, chemists were keenly aware that elements exhibited recurring patterns of chemical behavior based on their atomic number, the number of protons in the nucleus. These patterns could be understood in terms of the arrangement of electrons in the atom. The periodicity of elements, with similar properties appearing at regular intervals, was not a random occurrence. Instead, it was the result of the systematic arrangement of electrons in atomic orbitals. According to the exclusion principle, the arrangement of electrons in an atom is dictated by the need to fill available orbitals in a way that respects the principle that no two electrons can occupy the same quantum state. Electrons fill orbitals starting with the lowest energy levels, the so-called off-bow principle, with each orbital being occupied by one or two electrons, depending on the orbital's shape and energy. The fact that two electrons can occupy the same orbital but must have opposite spins, one with spin, the other with spin, is a direct consequence of the exclusion principle. For example, in the case of hydrogen, which has only one electron, that electron occupies the orbital. For helium, the second electron must also occupy the orbital, but with opposite spin, giving helium its stable, filled electron shell. As the number of electrons increases, the electrons begin to occupy higher energy orbitals, such as, and so on, until the outermost shell is filled. This filling order explains the periodic nature of the elements. For instance, the noble gases, such as neon and argon, have full outer electron shells, which is why they are chemically inert. The way in which electrons fill orbitals and obey the exclusion principle dictates the chemical behavior of elements and their placement in the periodic table. Pauli's exclusion principle also plays a crucial role in determining the chemical properties of atoms. The arrangement of electrons in atomic orbitals determines how atoms will interact with each other to form bonds. In molecules, atoms share or exchange electrons, and the types of bonds formed depend on the specific arrangement of electrons in the outermost shells of the atoms involved. The fact that no two electrons can occupy the same quantum state means that electrons must occupy different orbitals or have opposite spins when they interact with other atoms. This restriction shapes the types of chemical bonds that can form and is a key factor in understanding molecular chemistry. Beyond chemistry, Pauli's exclusion principle has profound implications for the physics of solids. In solid-state physics, the behavior of electrons in materials is crucial for understanding their electrical and thermal properties. The exclusion principle is central to the formation of energy bands in solids. In an isolated atom, electrons occupy discrete energy levels. However, when atoms come together to form a solid, the available energy levels overlap, and the discrete energy levels merge into continuous bands. The filling of these bands, which is constrained by the exclusion principle, determines whether a material is a conductor, insulator, or semiconductor. In conductors, such as metals, the outermost electrons are free to move within the material, allowing electrical current to flow. This behavior arises because there are available energy states for the electrons to occupy. In insulators, the outermost electrons are tightly bound to their atoms, and there are no available energy states for the electrons to move into, preventing electrical conduction. Semiconductors, which are used in electronic devices, have energy bands that are partially filled, allowing for controlled movement of electrons under the right conditions. Pauli's exclusion principle plays a fundamental role in determining these behaviors by governing the arrangement and distribution of electrons within the energy bands. The principle is also essential for understanding the behavior of matter at extremely high densities, such as in white dwarfs and neutron stars. In these astronomical objects, the density of matter is so high that the electrons in white dwarfs or neutrons in neutron stars are packed into very small volumes. The exclusion principle prevents the fermions in these objects from being squeezed into the same quantum state, providing a form of pressure that resists gravitational collapse. In the case of white dwarfs, this pressure is known as electron degeneracy pressure, and in neutron stars, it is neutron degeneracy pressure. Without the exclusion principle, these stars would not be able to resist collapse and would instead collapse into a singularity, forming a black hole. Pauli's exclusion principle also leads to the concept of degeneracy pressure in more exotic contexts, such as in the interiors of large stars or in the formation of black holes. When the density of matter becomes extremely high, the electrons or neutrons in the system cannot occupy the same quantum state due to the exclusion principle, and this creates a pressure that supports the star against gravitational collapse. In white dwarfs, for instance, this degeneracy pressure prevents the star from collapsing into a black hole. In neutron stars, the degeneracy pressure is due to the exclusion principle acting on neutrons, which are also fermions. This prevents the collapse of the star into a singularity and leads to the formation of a dense, compact object. In summary, Pauli's exclusion principle is one of the most fundamental concepts in quantum mechanics, and its consequences stretch far beyond the realm of atomic physics. The principle governs the arrangement of electrons in atoms and molecules, determining the chemical properties of elements and the structure of the periodic table. It also plays a crucial role in the behavior of materials, shaping the electronic properties of solids and enabling the development of technologies such as semiconductors. On a cosmic scale, the exclusion principle helps to explain the stability of white dwarfs and neutron stars, providing pressure that prevents these objects from collapsing under their own gravity. In many ways, Pauli's exclusion principle lies at the heart of our understanding of matter, from the smallest particles to the largest stars. In the early 20th century, the classical understanding of physics was being increasingly challenged by phenomena that could not be explained by the established theories of Newtonian mechanics and electromagnetism. The development of quantum mechanics was a revolution in scientific thought that radically altered our understanding of the physical world. One of the key contributions to this shift was the concept of quantum entanglement, a phenomenon that Albert Einstein famously referred to as spooky action at a distance. Despite its seemingly strange and counterintuitive nature, quantum entanglement has become a cornerstone of quantum theory and has far-reaching implications for our understanding of reality itself. Quantum entanglement arises from the foundational principles of quantum mechanics. The idea that particles can be entangled, meaning their properties become linked in such a way that the state of one particle directly influences the state of another, even if they are separated by Vast distances challenges our classical understanding of causality and locality. It was first proposed by Einstein, Boris Podolsky, and Nathan Rosen in a 1935 paper that introduced the famous EPR paradox named after the authors. They sought to demonstrate that quantum mechanics was incomplete by using a thought experiment involving entangled particles, but their paradox inadvertently highlighted the strange and profound implications of entanglement for quantum theory. Entanglement occurs when two or more particles interact in such a way that their quantum states become correlated. This means that the quantum state of one particle cannot be described independently of the state of the other particle, even when they are separated by vast distances. For example, consider two particles, A and B, that are entangled. If the properties of one particle are measured, such as its spin or polarization, the corresponding property of the other particle is determined instantaneously, no matter how far apart particles are. This seems to imply that information is traveling faster than the speed of light, which would violate one of the key principles of relativity. However, despite this apparent paradox, no information is actually transmitted faster than light because the measurement outcomes are random and only become correlated once the results are compared. One of the most important aspects of quantum entanglement is that it challenges our classical notions of locality and causality. In classical physics, the principle of locality holds that objects are only influenced by their immediate surroundings. Nothing can affect something else unless they are in direct contact or connected through a mediating force. Causality, meanwhile, dictates that events are linked by cause and effect relationships, with a cause preceding its effect in time. Quantum entanglement, however, seems to defy these principles. When two particles are entangled, the measurement of one particle's state immediately determines the state of the other, regardless of the distance between them. This instantaneous connection between particles appears to violate locality and causality, suggesting that the quantum world operates according to a very different set of rules than those that govern the macroscopic, everyday world. The implications of quantum entanglement were not fully understood until later experiments confirmed its existence. In 1964, physicist John Bell formulated Bell's theorem, which showed that no local hidden variable theory could account for the correlations observed in quantum entanglement experiments. Bell's theorem demonstrated that the predictions of quantum mechanics were incompatible with the idea that particles had pre-existing properties independent of measurement. This result led to a series of experimental tests designed to measure quantum entanglement and verify whether it could be experimentally observed. These experiments, which began in the 1970s and were refined over the following decades, confirmed that quantum entanglement is a real phenomenon, not just a theoretical oddity. In one of the most famous experiments, Alain Aspect and his colleagues conducted a series of experiments in the early 1980s that tested the predictions of quantum mechanics against those of local hidden variable theories. Aspect's experiments involved measuring the polarization of entangled photons, particles of light. The results were in agreement with the predictions of quantum mechanics, showing that the polarization of the photons was correlated in a way that could not be explained by classical physics. These experiments confirmed that quantum entanglement is not just a theoretical concept, but a real, observable phenomenon. The experimental verification of quantum entanglement opened up new avenues of research in both theoretical and applied physics. The realization that entangled particles could be used for communication and computation gave rise to the field of quantum information science, which explores the ways in which quantum mechanics can be harnessed to process and transmit information in ways that classical systems cannot. Quantum entanglement lies at the heart of several emerging technologies, including quantum computing and quantum cryptography. Quantum computing exploits the principle of superposition, which states that a quantum system can exist in multiple states simultaneously, and the principle of entanglement, which allows quantum bits or qubits to be correlated in ways that classical bits cannot. In classical computing, bits can be in one of two states, either 0 or 1, at any given time. However, in quantum computing, qubits can exist in superpositions of both 0 and 1, allowing them to process information in parallel. When qubits become entangled, the state of one qubit is correlated with the state of another, enabling quantum computers to perform complex calculations exponentially faster than classical computers. This could potentially revolutionize fields such as cryptography, optimization, and materials science. One of the most promising applications of quantum entanglement is in quantum cryptography, specifically quantum key distribution, QKD. Quantum cryptography leverages the principles of quantum mechanics, including entanglement, to create secure communication channels that are theoretically immune to eavesdropping. In QKD, two parties can share a secret key for encrypting and decrypting messages using entangled particles. If an eavesdropper attempts to intercept the communication, the entanglement between the particles will be disrupted, alerting the parties to the presence of an intruder. This form of cryptography is based on the fundamental principle of quantum mechanics, that the act of measurement disturbs the system, ensuring that any attempt to intercept the communication will leave detectable traces. In addition to these practical applications, quantum entanglement has profound implications for our philosophical understanding of the nature of reality. Entanglement suggests that the universe may be more interconnected than we previously thought. In classical physics, objects were thought to have independent existence, with well-defined properties that could be measured without affecting other objects. Quantum mechanics, on the other hand, suggests that particles are not individual entities with well-defined properties, but rather are interconnected through a vast web of quantum relationships. This interconnectedness of the quantum world has led to various philosophical interpretations of quantum mechanics, including the many worlds interpretation and the Copenhagen interpretation. The many worlds interpretation posits that all possible outcomes of a quantum measurement actually occur in separate, parallel universes. In this interpretation, quantum entanglement reflects the branching of the universe into multiple realities, with each possible outcome of a quantum event realized in a different branch of the multiverse. This interpretation challenges our classical understanding of reality, suggesting that the universe is constantly splitting into an ever-growing number of parallel worlds. The Copenhagen interpretation, on the other hand, emphasizes the role of the observer in determining the outcome of a quantum measurement. According to this view, quantum systems exist in a superposition of states until they are observed, at which point the wave function collapses, and a definite outcome is realized. The entanglement between particles in this interpretation suggests that the observer plays a crucial role in determining the state of the system, even at a distance, and that particles are fundamentally interconnected in a non-local way. Despite the fact that quantum entanglement challenges our classical intuitions, it does not imply that the laws of nature are violated. Quantum mechanics is, in fact, a highly successful theory that has been tested and confirmed by countless experiments. The phenomenon of entanglement is a natural consequence of the mathematics of quantum mechanics and reflects the strange but consistent behavior of the quantum world. However, it also highlights the limitations of our classical world, and forces us to reconsider the fundamental nature of space, time, and reality itself. In recent years, quantum entanglement has become an area of intense experimental research. One of the most ambitious goals is to create a quantum internet, a global network based on the principles of quantum entanglement and quantum key distribution. Such a network would allow for perfectly secure communication, with the potential to revolutionize fields such as banking, national security, and online privacy. Researchers are also exploring the possibility of using quantum entanglement for quantum teleportation, a process by which quantum information is transferred from one particle to another, potentially enabling instantaneous transmission of information over long distances. The implications of quantum entanglement are far-reaching and are still being explored. On the one hand, it has the potential to enable revolutionary new technologies, from quantum computers to unbreakable encryption systems. On the other hand, it challenges our deepest philosophical assumptions about the nature of reality, locality, and causality. Whether or not we fully understand the deeper implications of entanglement, one thing is clear: quantum entanglement is not just a curiosity of quantum theory, but a profound feature of the universe that has the power to reshape our understanding of the physical world. In the end, entanglement is not merely a theoretical construct, but a reflection of the interconnectedness of all things at the quantum level, forcing us to confront the very nature of the universe itself.